Hello everyone. Uh, let's pick up where we last left off at question 16. This is part 2 of solving the Feb-March 2022. Of course it's variant 2 because there aren't any other variants. This is AS level. So let's continue the last half because last time my mic off because I muted it from my headset itself. So let's go. In the reaction shown, the concentrations of both X and Y are reduced to half of their original values while keeping the total volume of solution constant. Okay, so the total volume is constant, but the concentrations are both reduced to the half. Alright. Simultaneously, temperature is increased. Alright. So which prediction is definitely true? So we're looking for the most perfect answer here. So this is gonna be appropriate for elimination. A smaller proportion of collisions between the particles of X and particles of Y will be successful. So this isn't totally true because although the concentration is half, but the temperature increased by a large amount, and temperature is the most important factor when determining their rate. Average kinetic energy of the particles of X and Y will increase. So as you know, the definition of temperature is the total average kinetic energy of the particles. So if you increase temperature, you're increasing the average kinetic energy. So it's true, it's correct. The rate of reaction will be unaffected, and actually in A you're not totally sure of the answer because you don't know the concentrations. There's a lot of factors to take in, so it's not definitely true. B is definitely true. C, the rate of reaction will be unaffected. No, since you're changing the concentrations while keeping total volume same, and you're changing temperature, so the rate is affected. The frequency of collisions between the particles of X and Y will halve. Again, no, it's not definitely true because you're increasing the temperature, so it's not gonna halve with the concentrations. No, you're increasing temperature, so the frequency of collisions will actually increase. It's not talking about the successful collisions. A student investigated the chloride of a period 3 element. This is what the student wrote down as a record. Okay. Compound of a white crystalline solid. Okay, that's... So it has to be something of... it's a chloride. Alright, let's continue. So it's not SiCl4. So that's a liquid. So it's out of it. PCl4 is also not a solid. So it's either Mg, Na... Al is also... It's not... Let's continue. Let's see. Dissolved easily in water to give a solution of pH 12. Okay, so it gives a basic solution, so it's not one of those AlCl, it's not even AlCl3, SiCl, or PCl4, because these give solutions of 2, because they form acids. This forms HCl, this forms H3PO4 and HCl, so it's like very acidic, so it's definitely not them. So it's one of these. When placed in a test tube and heated in a roaring Bunsen flame, the compound melted after several minutes heating. Alright. So it melted. Fine. So that's kind of weird. It dissolved easily in water. So we're seeing here that it's not easy to find a conclusion here, so let's go through the options. So this is definitely wrong. NaCl, no, NaCl is wrong, and MgCl are wrong. Why? They give solutions of pH 12. Let's revise the inorganic chemistry information. NaCl gives a pH of 7. This gives 6.5. This gives 2, like from in the range 1 to 4, something like that, because it's very acidic. None of these are correct. So one of the observations has to be wrong. This is like finding a conclusion basically using inorganic knowledge here. So here is just revision of the inorganic notes, revising the period 3 elements, their chlorides and the reactions with water and all that. Elements in period 3 and their compounds show trends across the period from sodium to chlorine. Okay, this is also still inorganic. We start organic right from question 20 onwards. So the first part, like first 10 questions I think or something like that, was physical, and then after that you start inorganic, and then the last 20 questions are all organic questions. So let's just put a timer here just for the, like, to see how much time we're taking, and let's go with maybe 30 minutes. Alright, which was correct, because here we're gonna try to not only solve, but solve under good time and use like smart techniques where possible. Okay. Electronegativity of the elements. Electronegativity, it increases across the period, and then the acid-base behavior of the oxides of the elements, so it goes from basic to amphoteric. So let's take the examples, the real examples: NaAl, and then the far left Cl. So NaO, Na2O, when you dissolve in solution, forms NaOH, which is very basic. Al2O3, amphoteric. ClHCl, acidic. So it goes from basic to amphoteric to acidic. These two align, it's C. The table shows the melting points of SiO2 and P4O6. Which statement explains the difference between the melting points? The bonding of the oxides changed from ionic to covalent. SiO2 is not ionic. It's covalent also, but has a joint structure. The metallic character of the elements decrease across period 3. I mean, that's true, but that doesn't explain I mean, technically it is true, but doesn't explain it. Alright, moving on. The oxidation number of the element increases from Si to P. So let's revise the period real quick. Na, Mg, Al, Si, P, SCl. Okay. So from Si to P, indeed, the oxidation number increases, but that still doesn't explain it. The structure changes from joint to simple. Now that's what explains it. So, I mean, if we skimmed through the options initially, it would have been faster, but here we're trying to explain it a little. So, alright, equal masses of CaCO3, calcium carbonate, calcium nitrate, barium carbonate, barium nitrate are thermally decomposed. Okay. The volume of gas produced in each experiment is measured under the same conditions. Which compound will produce the greatest volume of gas? So, right off the bat, I'm gonna eliminate carbonates. Why? Okay, so let's see. If you remember carbonates, they produce oxide, metal oxide, and CO2. But then if you look at nitrates, they form metal oxide too, but they form NO2 and O2, so there is more gas. That's like the quick thinking. So you already eliminated 2. And then when you look at the greatest volume of gas, the volume of gas is actually calculated by, so look, let's form the triangle Vn24. So the volume is the number of moles multiplied by 24. So the greater number of moles, the greater the volume. They're directly proportional, alright? So here, if the MR, that's the only difference here. So the MR is the only difference. So we're gonna look at the MR. If the MR of this increases, so we have the same mass, and then the MR increases, that lowers the moles because they are inversely proportional. Because if you have something that's the denominator, is gonna be inversely proportional. Alright, so the number of moles decreases, thus these gases decrease. So BA is wrong. CA will be the highest. Now that was good thinking. 21. Which row gives the correct comparisons between the solubilities of calcium hydroxide and barium hydroxide and the thermal stabilities? This is pure memorization. Solubility: calcium hydroxide is less soluble. The carbonates, thermal stability increases down the group, so barium is gonna be higher. Alright. 22. Which statement relating to the elements in group 17 and their compounds is correct? Bromine will reduce Ki to form iodine. Right. So let's see if it's actually reducing it. Ki has the iodide ion has -1 oxidation, or like the charge, oxidation number, and then iodine has 0. Every element has 0. It's getting actually oxidized, it's not reduced. Iodide ions react to form a white precipitate when added to silver nitrate. White is for chlorine. Iodide form yellow. Bromide ions react to form a white precipitate when added to, okay, again, it's not bromide, it's chlorine. Chlorine reacts with hydrogen to form a colorless gas, HCl. This is the correct one. HCl is colorless, but you know, when you're writing observations in paper 2, you say misty white fumes. Misty white doesn't mean they're actually white. Think about it like water vapor. Water vapor doesn't actually have a color. It just like looks misty and white. Looks like this gray gas, fumes. An excess of chlorine was bubbled into 100 centimeter cube of hot 6.0 mole decimeter cube sodium hydroxide. How many moles? Okay, so let's see the keyword here. Hot. This is also inorganic. We're still I'm surprised it didn't start organic yet. I don't know, but that's how it was most of the time. Okay, so let's go. NaOH plus Cl2 NaCl plus NaClO3 because it's hot plus H2O. The balancing, I suggest you memorize the balancing. It's gonna be hard to balance this without knowing the balancing. So here the balancing for chlorine is 3. This is 6. This is 5. You don't touch this one. You keep this the same, and this is gonna be 3. Alright, so let's look at the okay, hold on, I'll be back. Alright, so I was just getting my calculator here. Let's calculate the moles for the NaOH. 100. Okay, let me write it on the screen. 100 over 1000 because we use decimeter cube multiplied by the concentration. 0.6 moles. Alright, 0.6 moles of NaOH. How many moles of sodium chloride? Let's see the balancing. Okay, so the molar ratio is 6 is to 5. Alright, and then this is 0.6 moles and this is unknown moles. Let's cross multiply them. 5 multiplied by 6 by 0.6 over 6. 5 multiplied by 0.6 over 6, that's 0.5 moles. 23 is B. The product of the contact process is Z. It's SO3. We know that. That's general info. Which reaction or process leads to the formation of a gas that can neutralize an aqueous solution of Z? Okay, so SO3 is an acidic gas, makes H2SO4 in water. We know that it's acid rain basically, and it's from grade 10, the IGCSE days, the easy exams. Alright, so something that's basic, a basic gas. And look at the word gas, cause they try to trip you up in this part. Atmospheric lightning. It forms NO2, which is also forming nitric acid in water after it gets oxidized. Combustion of fuel in internal combustion engine. No, it forms CO2, which is also acidic. So these are wrong. The Haber process. Ammonia. Ammonia is an alkaline gas. So that's our best bet right now. Thermal decomposition of group 2 nitrates. You might think it's correct because it forms a metal oxide which is highly basic, but they said a gas. So D is wrong, it's C. 25. When ammonia is dissolved in water, a small concentration of ammonium ions is formed. Which row is correct? Number of electrons in one ammonium ion. Okay, so ammonium ion is NH4 plus. So when you have an ion and you're calculating the number of electrons, what I do is, what's the easiest method, you calculate the number of electrons like the ones you get from the periodic table. So hold on a second. Right, so we have here nitrogen has 7, and each hydrogen has 1. Alright, so now we have 7 plus 4, that's 11 electrons. This is not the ion, this is the like if it was a normal molecule like NH4, but then you have a 1 plus, so you remove one of it, it becomes 10. Change of the Alright, so the change of the bond angle from ammonia to ammonium. So ammonia has 3 H's and a lone pair at the top here. The lone pair is very strong, it's very repulsive, so it pushes them down more. So when you get rid of the lone pair and you form a bond with it, it's no longer that repulsive. So these go back a little bit more here, and the bond angle actually increases. So 25 is D. In this question, okay, so now we're into the organic chemistry. Alkenes and cyclic alkanes should be considered. Okay, so it's giving you a hint, so thank you for this. How many structural isomers of C4H8 are there? Alright, C4H8. So Rotodavats an alkene, so we can form the normal alkene. And one thing that helps is saying the name, because sometimes they're the same. So when you try to find the name, you realize that they're actually the same, but they might look a little different. Okay, so this butane, and then you can move the double bond one position here. Okay, I'm gonna stop drawing the hydrogens, it takes some time, and that's not optimal. So that's butene now. So now I have 2. Okay, so that's okay, so it's at structural isomers. We're not gonna consider cis trans, because we can here, but we're not gonna consider it. So that's it for the but1ene and butene. We can't really move it more, since that would be just the same as but1ene if we move it to the other side. Now we're gonna go with branching. So we form a 3 carbon branch, and we have 1 more carbon, so we can branch it out with this. So we can have the double bond here. So now that's prop. Wait, I'm gonna solve the methyl. So that was, so this is on the second carbon, so it's 2 methyl propene. So now we have 3 isomers. Alright, and then we can't really mess with this double bond anymore in the 2 methyl propene. That's it for now. Let's move on to the cyclic alkanes now. They reminded us of that, because we know in organic chemistry cyclic alkanes and alkenes are structural isomers of each other. So let's go with a cyclic alkane of 4 carbons. So that's it, that's one already. Each one has 2, so it's C4H8, so it's a structural isomer. Now let's go with a 3 carbon cyclic alkane and put a branch. So now that's 5th. We can't really make a 2 carbon. So that's all for the isomers. It's gonna be C. Which compound will decolorize Br2? So now here they've given you the structural formula, which is kind of tricky, so you have to look at the carbons. So this one looks to be completely saturated, but has a carboxylic which doesn't really react with the bromine, so we're gonna move on. Looks saturated, has a aldehyde. Don't confuse aldehydes with alcohols. So things to take care of when you're given a structural formula: aldehyde and alcohol. They look kind of similar, and you might trip up if you're solving under time pressure. And look for double bonds. You might miss them sometimes. Alright. Okay, so it's completely saturated, has an aldehyde, doesn't really matter. Okay, so here the carbons are missing. It should be a CH2 if it's saturated, but it has CH only. So that means it has a double bond here. That means it will decolorize, so let's put the tick here and go to the other one. Looks completely saturated, has an ester bond, doesn't really matter. The answer is C. Alkenes react with aqueous hydrogen bromide, so we know it's an electrophilic addition. The reaction proceeds via intermediate carbocations. Okay, so it's an SN1, so I'm just dumping info here. The more stable intermediate, the faster the reaction. Which sequence correctly shows an increase in the speed of reaction of the alkenes with hydrogen bromide? Okay, so we're looking for a more stable intermediate as we move from here to here. And how we get a more stable intermediate is by having more alkyl groups. Why? Because alkyl groups are electron push, like they push electrons away from them. So if you have an CH3, 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 and here a plus, each one is pushing electron towards this carbon. It's not completely giving it an electron, but it's pushing it towards it more, so it's reducing this charge more than if it was a CH plus. This is very unstable. The charge is very high. This is a bit lower, so it's more stable. So let's look at the options now. Ethene. So ethene, let's look at ethene. Has only one alkyl group, pretty unstable. Propene. Okay, so it's not the best upgrade, but it's definitely one, because instead of like a CH3 you have a C2H5 now. 2-methyl propene. Alright, so now that's definitely one hell of an upgrade. So you have about 3 alkyl groups pushing electrons towards you now. So now that's pretty stable, so it's a very fast reaction, so it has a proper sequence. Two methyl propene. Okay, so that's already very fast. So let's see what comes. Okay, no, that's very wrong, because you go from 2-methyl propene, which we draw here, as 3 alkyl groups, to ethene, which has only one. So that's pretty wrong. Propene to ethene, still wrong. Propene to methyl. Okay, and then to ethene. No. Okay, so that was a fairly simple question, although it needs some background knowledge. A reaction occurs when a sample of 1-chloropropane is heated under reflux with sodium hydroxide dissolved in ethanol. Which row is correct? Type of reaction. Okay, so let's see. 1-chloropropane heated under reflux with sodium hydroxide in ethanol. Okay, so one trick I use is NaOH has 2 types of reactions with ethanol and aqueous. Ethanol E, so elimination, and then aqueous is gonna be the substitution. So if it's ethanol E, elimination, so it's an elimination reaction. Then you move the product, so let's draw it out, makes it easier. Propane, 1-chloropropane. So we're gonna eliminate this, take a hydrogen here, make HCl, form a double bond. So it's gonna be propene. On to question 30. 9 minutes left. Okay, so we're going at a decently slow pace for explanation. The diagram shows the structures of 3 halogen alkanes. P, Q, and R can all be hydrolyzed. Which row is correct? Relative speed of hydrolysis and mechanism of hydrolysis. Okay, so the relative speed depends on first of all the stability and or the bond energy. So here is giving you the option between the Q and R only. So they're all the same except for this bond is different. So we're gonna look at the bond energies now. We know that as you go down the group 7, the bond energies decrease, like they're weaker. Why? Okay, so let's look. Iodine is a very okay, let's take Cl, and Cl is a very small, it's at the top of the group, and you know as you go down the group the atomic radii increase, and you have Br very big. So here is H and here's the bond pair, and here's bromine, and here's H, and here's the nucleus of bromine, and here's the nucleus of chlorine. Here's the bond pair. This is very far away from the nucleus, but this is very close. This has stronger attraction with the nucleus, with the bond pair, so it's a stronger bond, takes more energy to break. So the ones that gonna be faster is gonna be Q, because it has a weaker bond, so easier to break. Okay, so C and D are eliminated. Mechanism of hydrolysis, P and Q. So the one tertiary always show SN1, because they have a very stable intermediate. So P is gonna be SN1, no SN2. So B is wrong, A is the answer. 31. A sample of 2.30 grams of ethanol is mixed with an excess of aqueous acidified potassium dichromate. Okay, so excess, so there's oxidation happening here. The reaction mixture is boiled under reflux. Alright, so you're gonna make a carboxylic acid. The required organic product is then collected by distillation. The yield of the product is 60%. Alright, so one thing you have to consider here is that you're gonna go through an aldehyde first. You're not gonna go from ethanol to carboxylic acid immediately. You're gonna go through an aldehyde. So let's see, let's go through the question. So you're gonna go from ethanol plus an O to make an aldehyde. Then under reflux, I'm gonna get oxidized one more to get carboxylic acid, which is the product. So let's see the number of moles of ethanol. They gave us 2.30 grams mass over the MR of ethanol. Ethanol is CH3 CH2O5. So 2.30, so let's add that up. 12 plus 12 plus 3 plus 2 plus 16 plus 1, that's 46. Let's check once more, because I do a lot of silly mistakes. So okay, it is 46. 2.30 over 46, that's gonna be 0.05 moles. Alright, and then it's gonna give you 60% of the product. So let's take 60% of what we're gonna theoretically form. So theoretically we're gonna form carboxylic acid is gonna be ethanoic acid. No, I stuttered. Okay, ethanoic acid. Alright, so 0.05 multiplied by the mass, which is 12 plus 12 plus 16 plus 16 plus the total number of hydrogens, which is 4. So we have 3 grams. So 60% of that, 60 over 100 multiplied by the 3 grams, that's 1.8. So don't take the percentage of the moles, take the percentage of the mass that's theoretically formed. So percentage of theoretical mass, not moles. A mistake that people do is take 60% of 0.05 moles, then multiply it. That's wrong. The structure of tartaric acid is shown. 4 moles of substance X react with 1 mole of tartaric acid. What could be substance X? So 4 moles. Let's look at what we have for here. We have 4 of the hydroxy. Okay, so something that reacts with the hydroxy groups, but not as a carboxylic acid group. Doesn't react with the carboxylic acid. It reacts with mainly the OH. Sodium carbonate, it would react with the carboxylic, not with the OH. Sodium hydrogen carbonate, no. Sodium hydroxide, still. Only sodium actually reacts with OH, so it's gonna be A. It's gonna form ONA. Which compound gives both? An orange precipitate, so it's a carbonyl. An yellow precipitate, so it has a CH3 held with the carbonyl. Ethanol. That's very wrong, because it doesn't have a C double bond, or it doesn't have a carbonyl group. Methanal. That's still wrong because it doesn't have the CH3, so it doesn't give a yellow precipitate. It doesn't pass the iodoform test. Propanal. Okay, let's see. Still no. It doesn't have the CH3 directly bonded to this. Propanone though passes this and passes this because it have a CH3 bonded to the carbonyl, so D is the correct answer. Let's go to 34 now. Alright. Student suggests two uses of LiAlH4, which is a very strong reducing agent, even stronger than NaBH4. So NaBH4 normally wouldn't oxidize carboxylic acid, but this reduces everything. So it does reduce carboxylic acid. I'll give the product shown. Reaction 1, let's see. No, it does not break double bonds or anything. It doesn't do any of that. So reaction 1 is wrong, only reaction 2 is correct. This is something that hydrogen plus the platinum catalyst would do. That's a addition, electrophilic addition reaction. Compound X contains a single ester group. X contains 27.6% by mass of oxygen. Which pair of products could be produced by the hydrolysis of X? Okay, so we have to think about the structure of X. Alright, so 26.7% by mass of oxygen. So let's convert that to a decimal. It's easier to work with. 0.276. Okay, so the mass of oxygen in an ester, single ester group, so it doesn't have anything else. Okay, so the mass of oxygen in an ester is the 2 oxygen molecules over those 2 oxygen molecules plus the rest. So 12 multiplied by X, this is the carbons. Okay, so I had a voice crack. Okay, so that's 12 multiplied by X. X is the number of carbons. So let's take for example this. And so here we have 2 oxygens, 3 carbons, and the number of hydrogens is gonna be 1, 2, 3, 4, 5, 6, 6. So you see the relation between the number of carbons and the hydrogen, it's multiplied by 2. So the number of carbons multiplied by 2, that's the hydrogen, plus 2x. Alright, so let's try to solve this. Just I advise you to use the shift solve on your calculator. If you know how to solve it, that's gonna be a plus. If you don't, you can search that up and learn how to use it. It's pretty beneficial. Okay, so we didn't make it on time, but we're very close. So I take this as W. Alright. Let's solve this equation. So the number of oxygens plus 12x for the carbons plus 2x for the hydrogens equals to 0.276. Shift solve. So we have x as 6. That means the number of carbons is 6. Alright. So let's see. Butanol and ethanoic acid, definitely possible. It adds up to 6 at the end. Ethanol and propanoic acid, wrong. Adds up to 5. Methanol and methanoic, no, they add up to 2. Propanol and butanoic, that adds up to 7. That's still wrong, so A is the only correct answer. So here you have to if you don't know the general formula of esters, you can find it out mid-exam by making a random ester, finding the molecular formula, finding the ratios, and making a ratio up, and then forming this equation. This way of thinking is actually pretty repeated in different questions. It doesn't always relate to esters. It came once about a ketone. So yeah, you have to never stop thinking. What is the least number of carbon atoms in a non-cyclic alkane molecule that has a chiral center? Non-cyclic alkane that has a chiral center. Least number is gonna be, so let's see. Alright. So you're gonna have to have more than 3, because otherwise you're gonna have CH3s on both sides. So something more than 3. Let's go with 4. Okay, so we're gonna choose one of the. Let's go with this carbon. So if we have an H, we have to have another CH3, and still we have two CH3s bonded to it. So we still have to go bigger now. So we have to go to 1, 2, 3, 4, and then 5. Alright, so if we choose, alright, so still, actually, if we take this middle one, we're gonna have two CH2 5s here. Let's go bigger now. Now we move up to 6. So if we choose this carbon, we have a C3H7 and a C2H5 and then H here, and then we can add a methyl here. Now that's a chiral carbon. The total number of carbons are 1, 2, 3, 4, 5, 6, 7. 36 is A. A molecule of polymer contains the sequence shown. Which monomer could produce this polymer by addition polymerization? Alright, let's see. So let's look at this. This. Okay, so it looks pretty repeated now. So you just look at like the first two carbons and then you can try to cut it up from there, because usually the structure given is in this format. So you can look at the first two carbons and then you can, if it doesn't work, then you're gonna have to like try to spot it yourself. But here it's pretty easy. It has a chlorine on one side and the rest is hydrogens. It only has one chlorine though, so this is wrong. This looks correct. This has more carbons than is shown here. This is also wrong, so it's B. Now we're pretty close to the end now. Oh my god. Okay. 38. Compound Y is heated with mild oxidizing agent. Mild oxidizing agents are like Tollens reagent and Fehling's solution. One of the products reacted hydrogen cyanide forming 2-hydroxybutane-nitrile. Alright, so it forms a carbonyl. Because we know carbonyls react with HCN and KCN. KCN is actually the catalyst, and this acts as a nucleophile. Okay, so this is just info dumping. So it forms a carbonyl basically. So it has to be, and okay, so give you this butane nitrile. That means it has 4 carbons. This is bonded to the nitrogen, 2-hydroxy. So on the second hydrogen, you have a hydroxy. Alright, so let's see. So you're gonna initially have this chain, which is propan 1-ol, because it got oxidized to form the carbonyl propanal, and then butane hydroxybutane-nitrile. Lysopene and beta carotene. Okay, so when lysopene is converted into beta carotene, what is the gain or loss of hydrogen atoms per molecule? Okay, so let's look at the alright, so let's look at the difference. So the difference seems to be in this part, and this double bond is being broken. This one is unchanged. So let's look at the structures now. So you're breaking this double bond, so you're adding a hydrogen here, and then for this carbon you aren't adding hydrogen, you're forming a new bond with this. So this carbon is losing a hydrogen. So for each hydrogen atom you add, you're losing one. You add here, you lose here. So it's not changed, it's C. Okay, so which shows compound contains a C double bond O and an OH group, so a carboxylic acid. So let's look for the C double bond O carboxyl 1670 to 1740. Okay, so this is at 110, 120, 130. Okay, 40, 50, 60, and 70. Alright, so that has the alright, and then it has an OH at 2500 to 3000. So this has actually an OH of an alcohol, not a carboxylic acid. Carboxylic acids, the OH comes before the 3000 by a bit, so it's not D. And here the OH, it looks to be right actually, because it has it at 2500 to 3000, so it looks to be right, and it's broad. It's pretty broad, and it has the C double bond O here, and then here's the OH, so B is a good candidate. Let's look at A. Okay, so right off the bat looks weird, doesn't have the broad OH, so I'm gonna cancel this one out. Here's the same, it doesn't really have the broad OH, so you don't have to just know the numbers or see the table. So infrared spectroscopy isn't as easy as you think if you don't study it. You have to have like some knowledge of the peaks, how they look. So for example, the CH is a very short peak, it's a very sharp peak. The OH for the carboxylic is very broad. The nitrile I think is very sharp. Stuff like that. You have to know the key features of the graphs. So here the answer is gonna be B. So that was it. It was a fairly easy paper. Wish you luck, and see you next time.